So welcome to the most scuffed data structures and algorithms tutorial you'll probably ever come across. So I'll start off by going over a linked list. It's because I just think it's such a fundamental data structure that you need to know. If you can implement a linked list and some of its elementary operations, then you shouldn't have any trouble implementing stacks and queues either. You can implement those with linked lists quite trivially. And then later on, I might just do a tutorial as well on hash tables, and you'll be able to see how you can use linked lists to do some pretty neat stuff like collision resolution and things like that. And so, just to get some housekeeping out of the way before you follow along with this tutorial, I mean, feel free to follow along anyways, but if you're not familiar with structures or pointers or things like that in C, I think there are a ton of resources on the internet that you can use to familiarize yourself with that content. I just won't be going in over here. And I'll be explaining like a little bit here and there, but just not too much. There's a book that I just recommend to just about everybody for the longest while. It's called C and GUI Programming by Simon Long. And feel free to refer to that book or just skim through the book, at least the first half of the book. I think if you're comfortable with that material, then you shouldn't have any trouble following along here. So, alright, let's just get started then. I'll code along, and I'll be using some scuffed drawings and scuffed diagrams, and we'll be making a lot of errors, and just you'll be able to see how coding happens in general. And nobody's perfect, and so, yeah, we'll figure it out as we go, okay? So, just start by including the necessary libraries. So it's just these two that we'll be needing. Oops, keyboard ain't working. Alright, so let's get our main function out of the way. And let's declare our function. So if you don't know what a type def is, or you don't know about enumerated types in general, again, just refer to the book, and you should be good to go. So type def struct node, node. Okay. And so the first thing that a linked list needs, right, it's just a collection of nodes, essentially. And what you'll need is some data, right? And each node is going to have some data, and it's also going to have the memory address of the next node in the linked list. Okay, so that's the basic functionality of a linked list. And there are different types of linked lists, like circular linked lists, double linked lists. What we'll be doing is what's called a single linked list. So you can only traverse in one direction, but once you're able to implement a single linked list, I think implementing a double or a circular linked list is pretty trivial. And so, right, so this is our pointer to the next node. Bear in mind that we're reusing the struct keyword here because we're actually referring to this structure here before it's actually defined. Later on in the program, like after, you can just call node and it would know that it's this structure. But because the structure hasn't been defined as yet clearly, you need to explicitly tell the compiler, right? So you have to reuse the struct keyword here. Okay, and that's basically the building block of a node, right, that make up our linked list. And so you start off by initializing it, so node star head equals to null. And this head pointer, right, it's a pointer of type node. And it's the most important thing, essentially, I'd say, in linked lists, right? If you don't know where the head of your pointer is, you can't traverse at all. And I think traversal is just the most important operation, and it's just used all the time. So you initialize your linked list to just be empty at first. And the first operation we're going to do is just printing out our linked list, right? So we'll say void print list. And the function parameters this should take would just be node star head, and that's just about it actually. So there's a lot of confusion between students, particularly about node and node star star and which one to use and which one not use. So I'll attempt to explain that, but I want to just implement the print list function, and then I'll implement the insert head function, and then we'll be able to at least see what the difference is. Alright, so all we have to do is traverse the linked list and just print out all the data, right? So while, and we'll say node star current equal to head. Notice I'm not dereferencing anything, and I'll explain all of this in a bit. So while current is not equal to null, right, just print out everything essentially. Not sure how am I gonna do this, so I'll just print data and I'll use like an arrow, something like that, right? And we'll print current dot data. And so yeah, this is just gonna start out our linked list. Our linked list is already empty, so if we were to call, which I will do, we're gonna just call this function, it's gonna break out immediately, so it won't print anything. If you know of a way to print a null value other than this, please feel free to let me know, but I'll just do this for now. I'll just print null. Yeah, we're not printing anything. No memory address value or anything like that, just null. Right, to let us know that we've reached the end of the linked list. And so let's test it out. So we'll say print, let's put it here actually, print list, and you pass in the head. Remember, again, notice that we're not using the ampersand operator. I'll try to explain why in a bit, but if you already understand pointers fairly well, it should be straightforward, but I'll still go it over just in case. And so let's compile and run. So we've got a syntax error, so it's supposed to be standardlib.h. It's a header file. Oopsie daisy. There we go. I should resolve that issue, and there we go. So you can see it just prints null, right? Let's do it one more time. It says null. Great. So that works as expected. Now let's get into the meat of things. So insert head. Okay. Once you understand this next bit here, I think you're pretty much good to go for the rest of linked lists and for the rest of data structures and algorithms, to be honest with you. So insert head. What are we taking? We're taking node star star head. So okay, star star instead of star. Why? I'll explain that in a bit. And we're gonna need the data, right? And so let me go ahead and just segue into explaining the difference between star star and star. Okay, I've got this, not this. This is my recording. This said very scuffed tutorial. Right then, so I got this little bit of graphic that I was hoping would be able to explain the difference between the star and the star star. Alright, so if you're instantiating a node, right, your custom type, you just use node just like this, right? It's just a custom data type, and it's a physical node. Okay, that's clear enough, I think. If you're using a pointer variable, right, to your custom data type, which would be node, it would point to, right, the memory address of some actual node. Okay, so it would point to the memory address of some node you have somewhere, right? It's a pointer. Hopefully you understand what a pointer is and what they do. Now node star star, this is a pointer to a pointer essentially. Okay, it's a pointer to a pointer. And so when you dereference, for instance, this pointer here, let me use my highlighter. When you dereference this pointer here, this is the value you're gonna get. Okay, when you dereference this double pointer here, what you get is the pointer that it's pointing towards. Okay, so you're gonna get node star, right? And then if you were to say, like, where's the, can I type? I'm pretty sure I can type, I just don't know where it is. Is it this? I think so. If you were to say star star head, right, instead of, so star head, when we're dealing with the double pointer, would give us the node star, right? And star star head would give us the physical node itself. Okay, I hope that's clear enough. And why do we even need this, right? Because inside of the insert head function, we need to modify this pointer value. Alright, and if you were to just pass it in just like this, you have no way to modify the pointer variable itself, essentially. you can only modify what it's pointing towards, right? The memory address that it's pointing towards, but you have no way to modify the pointer variable itself. And so, which is what you need to do when you're doing a lot of operations with linked lists. So you need access to this directly, which is why you're using node star star and not node star. Okay, that was very convoluted, but let's just get into coding, and hopefully it'll become a bit clearer, I think. So we need a pointer. We'll call it new node, right? We need to create a new node, and let me just type this out. Then we'll explain what this is. Okie dokie. So it's a pointer, right? It's called new node. And we know that a pointer is just a variable that has the memory address of something. And so malloc, it's just a function that allows you to dynamically generate memory. So we're dynamically generating memory somewhere that's the size of node, right? So it's just large enough to hold our node structure. And malloc itself returned what's called a void pointer. If you don't know what a void pointer is, please refer to the book. And so we have to typecast it, right? So that's why there's always something in front of malloc. You can't just use a void pointer just like that. You have to typecast it to something. So this is where this node star comes in. You just typecast it. Okay, so we created our new node. Great. Now what? So new node. Whoa, new node dot next, right? Sorry, dot data. Let's do the data first. Would be equal to data. That's simple enough, right? And a lot of people tend to get confused as well if you're not familiar with structures. Why are we using this esoteric looking kind of syntax? It's the same thing as the dot, to be honest with you. So in your mind, if you want to think about it like a dot, sure, feel free to do that. Just know that the difference between the dot and the arrow, if you want to call it an arrow, is you use the arrow when you're referring by a pointer, and you use the dot when you're just referring with the structure itself, okay? So, but you can just think of this for all intensive purposes like a dot. So new node dot data, new node arrow data, same thing, right? And so, okay, so we've set the data, and now we need to know where is it pointing. New node dot next. Where is it pointing, right? So we know that when our main function gets called, we initialize our linked list as empty, right? So every single linked list is gonna be initialized to empty. And so if we're adding a new element to the list, it has to point to this old head that we had here, essentially. And so this is where we use star head, right? So it's gonna point to this pointer, okay? Remember, as I was explaining earlier, the difference between star and star star. Star star would just return the value of the actual structure itself. If there was a structure here, in this particular instance, in the first iteration of the program, there's nothing there because it's null, right? But star head alone would give you the pointer, this pointer value here, head, right? So I hope that's clear, or at least starting to become clear to you. And okay, so we know that, and then the next thing you have to do is you have to update the head itself, right? Update the head pointer and set it equal to the new node that you just created. So every time you insert something into the head, that newly created node becomes the new head, essentially. And so yeah, that should just about be it for that. So let's go ahead and try inserting this and running it and see how it works. And so, oh, and I think this will help clear up a little bit as well. So it's insert underscore node. Now pay close attention here, and %head, and then we pass in the data. Let's just say 10, for instance. Alright, so what's going on here? Why are we passing in ampersand? Remember, right? Node star star. It's a pointer to a pointer, right? And so it's still a pointer, and a pointer is expecting the memory address of some variable, and it's expecting a pointer to a pointer. And the head here, if we were to just pass in head just like this, it would, in this case, right, it would just pass null straight into here, which is what we don't want. We want the memory address of this pointer variable itself. Remember, right, typically a pointer variable, the value that it's assigned to is the memory address, some memory address somewhere, right? But it's still a variable, and every single variable has a memory address, right? I hope that's clear. And so what you're passing in is the memory address of the pointer variable itself, okay? And then that is being stored into the double pointer here, essentially. So it's a pointer to a pointer. Maybe if you can just write it down or something if it's not clear, but I'm not sure I can explain that too much more than that. And then notice here in head, right, if we're not passing in an ampersand here. Why? Because if we passed in the ampersand here, we'd be passing in the memory address of the pointer variable, but we actually want the value itself. Now bear in mind, right, if we had something like integer x equals 0, I don't know, and we wanted to modify this value x inside of a function somewhere, then we would need to pass in the memory address, right, of x. Okay, so we can actually access the physical value in here and change it. But in this case, since it's already a pointer, right, it's already a pointer, then you can just pass it directly here, just like that. And the value will just go, and it'll go straight in here. Alright, so let's go ahead and run this and see what we get. We have an error. Oh, right. So implicit declaration, let's see. Yeah, I don't know why that's seems a bit strange. Try writing this program again, running it. Unidentified reference to insert node. Ah, that's why. Yeah, so this happens from time to time as well. It's not insert node, it's insert head. Yeah, so you make mistakes from time to time in programming, and it's just up to you to figure out what went wrong. And a lot of the times, particularly with myself, it's just a lot of silly syntax errors here or there. And so this should work fine now. Well, it's not working fine, and we have to figure out why. And so the issue is obviously somewhere here. So while current is not equal to null, it's not breaking out of the... Oh, and it's not breaking out because we're not iterating the pointer. So current has to be equal to current.next, right? So this way you iterate as you go along. So the pointer would be updating itself with the next value, essentially, the next node in the list. And so they should work fine now. I hope. We'll see. There we go, it works. So let's add another one in, and just to make sure. And so we'll put this one here. And we'll put this to be 20. And let's just try to walk this through logically before we actually go into anything. Okay, so the linked list is just going to initialize itself to be null, right? And then the first thing we do is we insert a head. And it's going to have the value 20, okay? So 20 is going to point to null. And then we insert a head again, 10 this time. And so 10 is going to point to 20, which is going to point to null, right? And why is 10 pointing to 20? Again, if you pay close attention here, new node.next, right, is going to point to whatever the head is at that time. And then the head would update itself to be the new node, okay? And if that's not clear, I think it would be helpful to just go it over very slowly, and I think it should be pretty straightforward from there. And so yeah, you'll see 10, 20, and null. Great. So I think that's literally it, to be honest. If you understood everything up until this point, and you don't have any ambiguities about the double pointers or anything like that, or how we're even traversing the linked list, I think all of the rest of the basic operations we have to do should come to you fairly easily from here on out. And so if there's anything prior to this point that you don't quite understand, feel free to ask, and I'll try to clarify it. But if you made it this far and it's clear, you shouldn't have any issues going forward, to be honest. It's just more or less how good are you visualizing, and yeah, we'll see. So we'll do the insert tail operation next. So there are a couple of basic operations you need to know when it comes to linked list. So obviously you need to insert at the head, you need to be able to insert at the tail, you need to be able to remove from the head and remove from the tail as well. And that's enough actually to be able to implement stacks and queues. So even if that's all you know, you're already sitting pretty. And then from there, I think it's important to be able to insert at any position, delete at any position, and what's more, you should know how to reverse a linked list, and what's also important, you should be able to detect if there is a loop in your linked list. And with those basic operations, I think you can safely move on to if you'd like to implement a circular linked list and double linked list on your own, and explore linked lists in general if you'd like, but that's just about everything I think you'd need. So let's do insert tail. Alright, what's going on here? Again, so we're inserting some values, so pass in the double pointer, pass in the data, and there we go. And let me just grab this as well from up here. Yank that, and paste it here. Great, so we created our new node again. And so it's always helpful, right, to sort of visualize these problems, as I was saying. How good you are at data structures and algorithms is going to come down to how well you can visualize these algorithms and these data structures and how they actually operate. Of course, maybe your brain just works entirely differently, so I'm just talking about myself in particular. And so if I'm not able to see these operations in my head, I'll pretty much have a hard time. And so maybe if your brain works differently, then feel free to figure that out. But this implementation here, at least, is just how my brain works and what I think makes sense. Okay. So suppose we had 3 nodes, right? Suppose we had 3 nodes like this. So we know that the first node, this is the head, right? And it points to this one, and then this will point to this, and then the last node is gonna point to null, pretty much, right? Suppose this is our linked list. Now we want to implement our insert at the tail function. So we want to insert something here in this position, pretty much, okay? And so it's gonna be somewhere here then, I guess, is where we're gonna want to insert it. And so it makes sense then that we're gonna have to stop at the last node, right? When we're traversing, we want to stop at the last node, pretty much. Or at least the last node of the current linked list. And so once we stopped here, right, we can imagine we've already created our new node. So let's say this is our new node, right? And we know that the last node in a linked list has to point to null. So this is going to have to point to null here. So let's do that. Let's just implement that right straight away. So we have our node, right? So new node.next. Well, let's just do the data first, because so let's just put in the data, and then null. Great. It has to point to null, pretty much, right? We know that. Now, the only problem here is that the linked list is actually not complete, because let me just erase this. The linked list is not complete because this one's pointing to null and this one's pointing to null as well. What we need to do, right, is modify the next value of this node structure to point to the new node that we just created. So all we're gonna do, right, remember we traversed the linked list up to this point. So current would be here. It would be set to this one here, this node here. And we would just modify it to point here instead of null. It'll just point here. I don't know if you can imagine that happening. And so this is how we successfully inserted a new node into our linked list. So let's go ahead and do that. So we have to iterate over the linked list. So while current dot next not equal to null, alright, that's gonna take us to the last node in the linked list. Then current is gonna be current dot next. Okay. And so we're now current, right, is now the last node in the linked list prior to the insertion. Well, we've already created our new node already, but just think of it as the last node in the linked list, and then current dot next, right, as I was showing you in the diagram, has to be equal to the new node that we just created. Okay, and hopefully that's clear enough. And there is a fringe case that we need to account for, but we'll get to that soon enough. Let's just make sure what we implemented just works fine. And so we can insert head, insert tail. So we'll insert 20 and then we'll just insert 10 right after that. Let's see if this works. Oh, I don't know why I just keep making that little mistake here. So this actually up here, yeah. So current is not defined, so you always have to make sure you define these things. There we go, there it is. Should be good. There we go. So yeah, we started off by inserting 20, right? 20 into the head, and then we inserted this. But what happens when the linked list is empty? Let's see. Okay, we got a segmentation fault. So what the bloody hell is happening? You have to realize, right, how this current algorithm, if you want to call it functions, is not accounting for what happens if the linked list is already empty. Okay, it only works well, all good and fine, if there's already a value in the linked list, right? Because remember, we're collecting we're collecting the head, right? And we're trying to traverse to find the last nodes. Even if there's just one element inside of your linked list, as we had prior with the insert head, there was just one element in the linked list, right? It was still able to find and execute current.next, okay? But since it's just pointing to null, there's literally no structure. There's no such thing as current.next, right? Because if you remember, star head here, it's pointing to null when the linked list is empty. It's not pointing to an actual node structure. So current.next, it doesn't exist, right? So it'll cause a segmentation fault in your program. You need to account for the fringe case, essentially. And so we can just do that here very quickly. So we can say if, right? Do an if statement at the very top. And you'll say if head, star head, is equal to, or if you'd like, I think it might be a bit easier to do this way because there's another piece of notation that can get a bit tricky. I'll explain it later on, but it goes something like this. You have to go star head, right? You kind of have to get the structure first and then point to something else. But this is just like so unintuitive, and it's not necessary at all. It just complicates things, especially if you just want to keep your code as simple as possible. So what I would advise you to do here is just to grab the current head and throw it inside of a pointer. Sure, it might take an extra line of code, but for simplicity's sake, let's just do that. And right, so we need to check, right, that is not null. So if current, so if it is null, right, if current is equal to null, that means, right, that the linked list is essentially empty. And when the linked list is empty, all you want to do is just insert at the head, pretty much, right? It's the same functionality as inserting as the head. So you can say new node. So new node.next, it already points to null, and it already has the data as well. So essentially all we'd have to do is update the head, right? Yeah, you just update the head of the linked list to be equal to the new node. Then you just break out. I think that's sufficient. It's already pointing to null here. And yeah, so all you have to do is update the head. I think this is okay. And let's go ahead and try running this now. And there we go. Right. We were able to insert 10 at the tail, and let's try it again. Insert tail. Oh, also, I probably should mention that just pay attention to this return statement here. You just want to break out of this function as soon as you're done with your fringe case, okay? You don't want it to continue executing. So we insert 10 at the tail, right? And let's say we insert 20 at the tail afterwards. So it should be 10 pointing to 20. Yep, there we go. All right. Hopefully that was clear. And so the next thing we're gonna do, so we did I don't consider print list to be a primitive operation, but okay. We did insert tail and we did insert head. So we should do now the next pair, which should be deleting at the head and deleting from the tail as well. Right, let's do delete head. Right, great. And once you know insert head, insert tail, delete head, delete tail, you're pretty much already well on your way. And I'd obviously encourage you to try to implement these functions on your own as well, and think through what exactly you're doing and try to visualize what's going on. I think that's the only way to actually learn. Alright, so we're gonna need, again, our double pointer, and that's pretty much it, right? We're just traversing, we're not have to do anything else other than that. And so let's try again visualizing, because this is what helps me. It might not help you, but it's what helps me, okay? So let's say we had a linked list like this, very simple linked list. Points to null. So this is kind of what I see in my head, but I just have to draw it out to get the point across. Might be helpful if I learn to use some kind of animation engine or something. Okay, this is fine. Our Scuffed tutorial. So this is the head, right? And we want to delete the head. Alright, and this is in the case where the linked list is not already empty. Obviously, if your linked list is empty, you want to check to make sure that it's, you're not deleting anything and there's nothing there. Deleting something from an empty linked list, not possible. Okay, so this is our head, and we want to remove this. We just basically want to chop this out, right? And this would be our new head, essentially. Okay, so the next pointer, so if we start off by collecting the head, the position of the head, or a pointer to the head, the next one is going to be our new head, right? And then we just have to free the memory associated with this, and it's as simple as that, I think. So delete head, right? So we need a pointer. We'll call it current head. Let's call it current head. Okay, so we got the current head. Now what we need to do is update the next head, right? We need to basically make the next element, or the next node, to be the new head, essentially. Since we're chopping off the original head, the element that follows, or the node that follows, should become the new head, right? And so star head, so we're updating the head, should be equal to, I think it makes sense actually to, should I free this first? Yeah, that's what I'm wondering to do, if I should free this first. I don't think it makes a difference, but we'll see. So we'll update the head to be current underscore head dot next, right? And then we'll free current underscore head. There we go. And let's try running this and see if we run into any problems. But I think that just about makes sense. So we'll delete head. In this case, 10 would be the head, so we should just print out 20. Well, let's see. Yeah, so it works fine. But again, if we try calling this function again, it should delete the 20 as well. Yeah, so now it's empty. And then if we did it one more time, we should get an error. Yep, segmentation fault. Right, so there's nothing to delete in that particular case. So you do need to check for that special case, and you can check right at the top here. Just go here, and you'll say if current underscore head is null. Alright, so if the linked list is empty, then just print something and then break out of the function, essentially. Linked list already empty, something like that. Then you just return So now it should just tell you that the linked list is empty. Yeah. And then it returned null. Great. So we can delete from the head. Hopefully that was clear. I'll just go it over very quickly again then. You grab the current head. You update the new head, right? The head pointer to be the current head dot next, right? Which again in our diagram would be this. So this is becoming the new head. We're getting a new head and it's going to be this, and then we're freeing the memory associated with this pointer here. So this is gone now, and this becomes the new head. So simple enough, I'd hope. How do I add a new page? There we go, just in case we need more space. Okay, so we can delete from the head. The next thing we have to do is to be able to delete from the tail. Okay, so void delete tail takes pretty much the same function parameter. I'd rather put it here actually. Yeah, just so they're kind of grouped together. There we go. Alright, so let's try to, again, use our little diagrams to figure out what we need to do. So, we'll say we've got 3 nodes. This is our linked list. And this will point to null. Null, essentially. And so, if we're removing from the tail, right? Removing from the tail, we need to remove this element here. And how can we get access? I keep calling it element, but you can call it what you can call it structure, you can call it pointer, or whatever. Node is probably the better term. I'm just saying element for some reason. So we need to remove this node here, right? But in order to remove this node, we need to stop here, right? That makes sense because how a linked list is structured, we only have access to the next element in the linked list. So when we're traversing, we have to stop at the second to last node. Okay, we don't want to stop at the last node. We want to stop at the second to last node. And this would give us access to this node pretty much. And we'd be able to modify where this is pointing. So instead of pointing to the last node, it'll point to null, and then we can just free this off, and we'll essentially remove it from the linked list. I think that's fairly simple. So now how are we gonna stop at the last node? Now we're already familiar with, how do I type again? I think it's this one. We're already familiar with current dot next, right? So we typically say current dot next not equal to null, and you know already that this would take us here, right? This would stop us here. Where is it? Here. It would stop us at this node, but we don't want to stop at the last node. We want to stop at the second to last node. So actually what you do is you say current dot next, and you can actually nest them like this. And so it'll stop here instead. So it'll check current dot next is not equal to null, right? Current dot next not equal to null. So essentially we'll be stopping at the second to last pointer. And that's how we'll be able to modify this value here. Alright? Okie dokie. And so, again, let's just say node star current. Okay, so we got the current head, and we can traverse the linked list to the second to last element. So, well, current dot next not equal to null gives us the second to last element. Then you just iterate through the linked list. Fairly straightforward. So up until this point, you have the second to last element in your linked list. So the next thing you want to do, right, since we're here, is you want to change where this is pointing to. Instead of it pointing to null, it's gonna have to, rather, instead of it pointing to the last pointer, it's gonna have to point to null. Okay, since it's now essentially going to become the last element in your linked list. So yeah, so we'll say current not next equal to null. Okay, and we need to free this obviously, so we can create another pointer. We can say node star temp is equal to current dot next, and yeah, you can just free temp from there. That shouldn't give you any problems. Okay, and let's try it now. Obviously we still gotta cover all our bases, ensure we're not missing anything. Okay, so this one inserts 10 at the tail, 10 at the tail, so 10, 20. So if we remove, is it delete tail? Did I mess up the convention? Let's see. Yeah, it's delete tail. Okay, I managed to keep it consistent for once. Okay, so this should just give us 10. So that's the linked list is already empty. Okay, so let's put in another element here, and we'll be able to go over why it's giving that error. Actually, it shouldn't be giving that. Let me make sure this program was... Yeah, it shouldn't have been giving that. So first off, there's a syntax error. So typically, you have to make sure your file is saved. And we have, what, 3 R's here? I think that's the problem. Where are we? It's all the way to the top. Yeah, here it is. Okay. That should be fine. Let's see. Okay. So it did successfully delete the 20 off of it. And delete tail again. Oh, right. Too many parameters. Okay, should be fine. Alright, so this gives a segmentation fault. Alright, so what the bloody hell is going on here? Why is it giving a segmentation fault? So in our original... I don't want to draw it, I'll just draw it again. So we started off originally with a linked list that looked... I'll just say n for now. We had 20 here and we had 10 here. We called the function, right? And it stopped here. It stopped here and it checked. It accessed here. But what do you do when there's only one element inside of your linked list, right? This is a fringe case that you need to consider, because you can't, there's nothing prior to here that you can traverse to stop at to point to this node, right? You're already at the node that you need to delete. And so what you do in this particular case is you check the fringe case. So if current, right, the current head dot next is equal to null, right, in this particular case, that means that there's only one node in your linked list. And so the current node you're at is the one you need to free, essentially. Hopefully that makes sense. This is why you need to take care of that fringe case. And then obviously you need to take care of the case when the linked list is already empty as well. And so you just print out an error message like we did previously. So let's go ahead and fix that. So where are we? Delete tail. Here we are. So we need to cover our fringe case, right? And so we need to check, essentially, if... Why is the indentation so weird for some reason? I don't know. Oh, that's why. Okay. So if current dot next is equal to null, right? That means that there's only one node inside of the linked list. Okay? And what we want to do in that case is update the head of the pointer to be null, right? Because the linked list is now going to be empty. And then you free current. And then you just break out like this. Hopefully that makes sense. So you update the head of the pointer to be null, right? Because you just removed the last element in the linked list, so it should be empty now. And then you just free that bit of memory there. And then you want to take care of the next fringe case, actually, which is if current is equal to null, then you want to print. And I'll show you something pretty cool as well, which actually really does test. These sort of implementations really do test your understanding of what you're doing, because you can't just, there's no way you can implement this and not understand what you're doing because so much can go wrong and you'll be like, huh, what the hell went wrong, right? So you really do have to know these little things, or at least to be able to, after a while with a bit of experience, it just comes to you, I suppose. But at first, it's easy to run into these types of errors and wondering like what's happening. But I'll show you. So, linked list already empty. New line, and then we'll just return. And that should take care of that issue here. Okay. Nope. Syntax errors. I put this outside of the double quotes. There we go. Okay. There. It's null. And let's see. We're deleting twice, so we need to delete one more time. Can I just paste? No. Just delete that. Yank this. Paste this here. Alright, so we're deleting again, right? So it should just give us the... yeah, linked list already empty. Great. Now, let me change something really, really subtle in this code. And it's like a really honest mistake you can make as well. Imagine for a second, right, that you just copied this bit of code here, right? And you put it at the bottom here. You're probably like it makes no difference, right? Like, what difference does this make putting this at the bottom here? Well, let's see. Segmentation fault. Well, like, what? Here's what's actually happening. So you're checking, right? First thing that you're checking, and where is it? It's easy to lose track. Okay, so the first thing you're checking is if current.next is equal to null. Now, when your linked list is empty, remember that it's pointing to null. It's not pointing to an actual node structure. So there is no current.next, right? There is no current.next, so it's gonna just give you a segmentation fault. Which is why it's very, very important to cover this base case first. You need to make sure that check that current is, if it's null, right, then you know the linked list is empty. Hopefully that's clear to you why that segmentation fault happened. And if you're getting segmentation faults in your program, you really do have to understand what's happening underneath the hood in order to be able to resolve them. Otherwise you'll just be running around like a headless chicken, I think, trying to figure out like what went wrong, right? And maybe it might just be something as innocent as that. You know, there might be, your logic in your code might be completely good, but just like one little thing, you know. Okay, so we just about covered, let me just write down again what we covered. So we covered insertion at head, insertion at tail, deletion at head, deletion at tail. And you can go do some research into stacks and queues at this point. And you can know, for instance, stacks follow a last in, first out principle, and you can implement it with a linked list. So if this were your stack, right? It's the last element in, it's the first element out. Does that sound familiar to you? Last element in, first element out. We're just removing the head of the linked list. That's it. Okay? That's basically, and they call it push and pop. So all you have to do is rename the function from insert head to push or pop, pretty much. Okay, so you should be able to implement stacks and queues pretty easily if you're following along up until this point. The next operations you have to be able to do, obviously, is to search a linked list, which would just be basic traversal. And you also need to be able to know how to reverse a linked list. I think that's an important operation. You should be able to know how to find the middle of a linked list as well. Again, though, if you're thinking, right, you should already be able to come up with solutions to these problems on your own. Or how would you go about finding the middle of a linked list? Like, just think about it, right? Maybe you'd use a double linked list, and you can approach the problem this way, for instance, right? Oh, and a double linked list, by the way, if you don't know, is that instead of it just pointing to the next element or the next node, it also points to the previous node as well, right? And so you can do some pretty cool things, like for instance, like so. So yeah, you can know where the head of your thing is. You can also have a pointer to the tail of your element as well, and you can count forwards and you can count backwards as well, and you can meet in the middle. Like, you can get really creative with what you do. It really just comes down to what you can come up with. But yeah, I'd always recommend students to try and implement these functions on their own and see whatever crazy things or ideas they might come up with. But alright, that was a bit of a segue into something else entirely. But let's talk about the inserting at a specific position and deleting at a specific position as well. So yeah, so these are just some generic functions that you should know. So that would be 6 complete elementary functions. And then maybe I can go over reversing a linked list as well. But I'm already getting pretty tired, to be honest. So maybe I'll just do that in a separate video. I'm already wanting to have some lunch. So let's just do the insert at a specific position and delete at a specific position. Okay, kind of messed up the pages. Alright. So again, we're gonna just... Okay, maybe that's too much. Yeah, this is fine. And this will point to null. Great. So how are we gonna approach this problem? Say for instance, right, I want to insert a node at position 0, 1, 2. Here. Why is it giving me arrows though? I really have no idea. Oh, that's why. Oh, let me use like red or something. Yeah. So suppose that I wanted to insert something in this position here. How would I go about doing this, essentially? Let's think. So the first thing I'd want to do, right, is I'd want to obviously create my new node. So let's do that. So we'll try to take this one step at a time. Void position insert. I guess we can call it that. And obviously we need to be able to traverse and modify, and we need the data, and we need the position that we're inserting at as well. Great. And so node star new node, all of this should be, you know, well known by now. It's pretty much just the same thing. Size of node. Okay. So we created our node. Great. And new node dot data equal to data. Good. Now we got our node. Great. What we need to do, let me just put in some arrows here, here, and here. So we want to insert this node in this position, pretty much, right? We want to insert it in position 2. So what we have to do essentially is change where this node is pointing, right? So if you can imagine in your head, instead of this node pointing to this node, it has to point here to the new node that we just created. Alright? So already we can tell that we need to stop. When we're traversing, we need to stop here. Let me use a different color. Let me use like yellow. We need to stop here. Okay? Because we need to be able to modify the next attribute of this element. So instead of it pointing here, right, it's going to point here to the new node that we just created. And then the new node, in turn, is going to point here. And remember, once we change that, then this will just disappear. And so essentially, if you look at this, it's a linked list, right? It's just continuing. So we've inserted our new node at position 2, 0, 1, 2, right? It's in position 2. How cool is that? Hopefully that was easy enough to follow along. And so how do we actually implement this though? So again, let's go in here and say current. Whoopsie daisy, node star. Let's grab the current head. And let's use a for loop this time. It might be just, you know, a bit easier conceptually at the very least. So we have our incrementer. And so now there's two very important cases that you want to check for here, actually. The first one would be current not equal to null, right? This would essentially mean that you're out of bounds, right? If you're traversing through your linked list and current somehow equals to null at some point, it means you've reached the end of the linked list, right? Because remember, null is always the last value in the linked list. And so you don't want to keep going. You want to break out immediately. So then you'd use an AND. So as long as that is true and this other condition is true, and so it's gonna be as long as I is less than position minus 1. Okay, and so again, we said that we wanted to insert at position 0, 1, 2. We wanted to insert here, and so I is gonna count up to position minus 1, and so it's gonna stop here, pretty much. Alright, so I is gonna go 0, I is gonna go 1, and we're gonna increment, obviously, and then once it gets to 2, the condition is gonna go to false, right? Because position is 3, right? And our position is 2, rather, 0, 1, 2 in this particular case, and so it'll just be 1, right? So as soon as it reaches to 1, it'll stop. It'll break out of the loop. Okay, and then we just want to say current is equal to current dot next, right? And so we'll essentially be stopping here. Great, hopefully that's clear so far. And so what do we do next, right? Again, currently this is pointing here. We don't want that. We want to change current dot next, right? Current dot next to be the new node, to point to the new node that we just created, right? So now this is pointing here, so we can erase this now. But remember, the new node is not pointing to anything as yet. So the new node, right, this is where it might get a little bit tricky. The new node has to point to current.next, if that makes sense. If we were at current here, right, current.next would be this node here, right? The new node has to point to that value. So what we do is we can say node star temp is equal to current.next, right? So we've stored that value in a temporary pointer. So we have this value, we have this node here now stored, right? It's current.next. Then what we can do is say new node.next is equal to temp. So it's gonna point straight back to the first one. I'll just use black in this case. And there we go, it should be completed. Now again, obviously there are fringe cases that we need to take care of here. And again, if you were following how we were doing the delete at the tail, what happened when we tried to stop just before the element we wanted to modify, what happened, you'll see that it's the same thing is going to happen here again if you were following there. But okay, so this should be fine, and let's just take care of one of the obvious fringe cases, is when the linked list, actually no, one of the obvious cases would be when we're out of bounds, right? That would be one of the obvious cases, when we're out of bounds. But I'm wondering if to just let the errors happen and show you, or just do them right here. Let's just make sure this works first, and then we'll go back to that. It was position insert, right? I hope so. Get rid of this, get rid of this, get rid of this. Okay. So we'll say position insert. This should work. So we're inserting at position 0, position 1, right? So if you want to imagine, we've got 2 nodes currently. 0, 1, and then this points to null here. Suppose we wanted to insert it here, in this position, in position 1, right? So it would just come like this, and it would be in position 1 now. So let's try that case first, right? So let's put 10, 15, so just like progress, and then position 1. Make sure I save this. So yeah, more syntax errors. Okay. Let's see, where are we? Oh, I forgot to increment. Okay. New node is undeclared. Let's see. Oh, why? It's a new. What is going on? Okay, as I said before, a lot of the errors I make are just very small. Or a lot of the errors you might make as well, who knows. But I know, but I can speak for myself. A lot of them I tend to make are just really simple things like that. Okay, so it's fine, it works. So, especially when I'm tired, oh good lord. So, we've got 10, 15, and 20, alright? As we were expecting previously with this diagram here. So we're inserting 15 in between 10 and 20. Good job. That works. And so the next thing I think we should try is what happens if we try to insert it at position 2, right? Position 2 would be, well, here. This is position 2. 0, 1, 2, right? This is position 2. What happens? Does it work? Yes, it works. Why does that work? It might seem a little bit ambiguous to you, like what is actually going on at position 2. But it's the same thing, pretty much, right? So if you want to insert it at position 2, we create the new node, same as before, right? We stop here, right? And then we change the pointer. So this would come and point to here instead, right? And then, remember in the program that we were saving in temp, this pointer here, we were saving this in a temporary pointer as well. And so then this would just end up pointing to that. Boop, that would go. And that's how we got it to insert into the last position. Okay? Now, let's get into the funky stuff. What happens when we try to insert it into position 3, for instance? Well, that's obviously out of bounds, right? Segmentation fault, obviously. So we're gonna have to take care of that. So you can come up here. Actually, you don't have to go up anywhere. You can come here, right? Because remember, our program is going to break out automatically when it detects that we're out of bounds, essentially. Right? So we can say if, we'll do the first obvious case. Current is equal to null. That's the first obvious case. Well, it's the only obvious case, I think. So, printf out of bounds. There we go. Out of bounds. New line. Keep forgetting that. And don't forget your return statement. And you should get out of bounds. There we go. That works fine. Now, there's one other case that we do need to consider. And what if there's only... Or what if we want to insert something at the head of the linked list? Right? Position 0 is a special case in this particular algorithm, because remember, we need access to the previous element, right? But there's no access to the previous element to point to position 0, if that makes sense to you. And so we need to handle this as a special case. And if we go down here and try to insert something at position 0, or the head of the list in this case. Okay. It did insert something. It definitely didn't insert it well, though. Right, so it put the 15... Oh, yes. So this is what's happening. So... The loop, right, is going to insert it here in this position, pretty much, as to be position 0. This is where it's going to put it. It's not going to actually be able to put it here directly, again, because there's nothing before here that we can reference to. So it's going to drop it in the middle here. So, we need to take care of that. Where are we? Okay. We can say if position is 0. We'll handle it as a fringe case. Return. Yeah, and I hope you understand as well why it was inserting it into that case, because remember, we're inserting it at position 0, so it's going to break out directly at the head, right? It didn't increment. This case is going to automatically evaluate to false, and it's not null, right? It's not null, so we're not out of bounds, and it's going to come here and try to insert it that way, okay? And remember that normally current has to be the node just before you're trying to insert, okay? And so in this case, current is automatically set as 0, and so the program, for all intents and purposes, thinks that you're trying to insert at position 1 since current is 0, right? And we've already been over what this bit of code does, and so hopefully you can understand why, if you were still wondering why the 15 was in the middle, as if you were inserting it at position 1, and why we need to handle the special case. Just thought I should probably elaborate on that just in case. But okie dokie, how do we handle, or how should we handle our fringe case then? What do you guys think? Obviously, right, if we're inserting at position 0, we already have access to this, right? We already have access to this, so it just has to point to this, and then we update the head, right? Hopefully that's clear enough. And so we have access to this old head here, so we'll say new node dot next is equal to, right, current. Okay, new node dot next, the new node dot next would be equal to the current head, so it's pointing to the current head, and then we update the head to be equal to the new node. Okay, there we go. Perfect. And guys, I'm just really tired at this point. I really hope that I've equipped you with enough to be able to go ahead and implement the position delete on your own. Like, I swear, if you could implement position insert, there's no reason you can't implement position delete as well. Just do the same thing we were doing, try to reason it out, try to find your fringe cases, and cover all of your bases. And if you're having trouble inserting position delete, let me know. I'll just make a separate video doing that. And then you should try to reverse a linked list as well. I think you should be able to reason within yourself and figure out how to reverse a linked list. And yeah, but I'll definitely just at some point later on make a video on how to reverse the linked list and to find a loop in the linked list. And yeah, that should be it from my end. Hopefully some of you would have found this very scuffed tutorial somewhat useful, but I'm very hungry now and it's time for lunch, so have a good one, guys.